So what I'll do is I'll just sort of whiz through it. I'll pause every so often if you want to ask me any questions. So semiconductors, those of you that do chemistry will be familiar with energy levels in more detail than you actually need in physics and semiconductors. But it's all about the outer energy level, and that's what we'll look at, what's important in semiconductors. So in atoms, we know that electrons are around the outsides, but we know now that they can only exist in discrete energy levels, so certain energy levels in each, and energy levels in each atom are individual for each atom. And each level has a certain energy associated with it. And you've talked about that in spectra before, so you talked about the difference in energy between them. E equals HF, you can find the frequency of light given off if something jumps down to a lower one and gives off a photon. So these levels can be empty, full, or partially filled. And the arrangements of electrons in these levels affects the properties of atoms. So two things that you already know about, insulators and conductors. So for something to conduct electricity, it has to have electrons that can move. So when an outer energy level is completely full, that's a very stable structure. Those of you in chemistry, again, will know a bit more detail about this, but all you need to know is a full outer energy level is very stable, and very rarely can you get electrons to move around in that. They just want to stay in that full outer energy level and they don't want to move, okay? So in an insulator, the outer energy level, the valence level, is completely full, okay? And the electrons are held there, they cannot move. Okay, there are some situations where you can force them to move, but generally they are insulated, the electrons cannot move. So what we have there is we've got a full energy level, and we call that the valence level. It's the outermost full energy level. Okay. Above that, so a higher energy, we can have a conduction level, okay, a conduction band even. And that's where you can have some electrons can be occupying it. And if some electrons are occupying the level slightly up from that, then that means electrons can move around and conduct electricity. Okay, so conductors, the outer energy levels have very few electrons. They're loosely held and are free to move to neighbouring atoms. This is what causes electric currents to be able to flow through them. Semiconductors, however, and here's an example of a semiconductor, silicon, I think. Semiconductors have like an in-between state. Okay, so they haven't got a full outer energy level, but they've got a half full outer energy level, which again is quite stable, but not as stable as a full outer energy level. So electrons do like to they like half full energy levels and like full energy levels. So they're not particularly easy to move from this structure either. They're easier to move than in an insulator, but they're still not quite very easy to move. So this still requires quite a lot of energy to force one of those electrons up to the conduction band and to be able to start moving around. Okay. So in semiconductors, like a silicon atom, the outer energy levels are partially filled. They tend to bond with other silicon atoms quite strongly. They can conduct electricity under certain circumstances, which we'll talk about later. So it's basically under circumstances where you can give them energy, enough energy to then jump up to a higher energy level. Band theory. So instead of talking about individual atoms with individual energy levels, what we tend to do is we tend to basically stretch out those energy levels in lots and lots of different atoms, and we call them bands rather than lots of energy levels. So in atoms, electrons exist in energy levels. When we have lots of the same atom together, the energy levels can be grouped together. We call them energy bands. And the highest occupied band, that's a fully occupied band, is called the valence band. So that's one if it's full. And the one above that is called a conduction band. Okay, so that's quite often, it's either empty or got a few electrons in it that can move. These are the two bands we're interested in this topic. So we don't really care about what's happening further down in the atom. We're looking at the two the outside energy levels. The valence band and the conduction band are separated by a band gap. That means basically an amount of energy it requires for anything to move from the valence band to the conduction band. Okay? And each atom has its own different band gap, depending on how much energy it requires for the electrons to jump from the valence band into the conduction band. So this band gap is related to how much energy is required for an electron to jump from the valence band to the conduction band and therefore conduct. For a material to conduct, it must have electrons in its conduction band or spaces or holes in its valence band. So electrons in the conduction band, easy enough, they can move around the space for them to move. The valence band, if you have full valence band, then there's no movement at all. If you take one electron out of there, then you've got a spot where other electrons can move into it and leave a hole behind. And another electron can move into that hole and leave a hole behind. So you can have movement of electrons within the valence band if you take out an electron, if there's a space for it to move into. Okay. So band theory, insulators and conductors. So I basically said about this. In an insulator, the valence band is full and no electrons exist in the conduction band, and it requires a lot of energy for electrons to move from the valence band to the conduction band, so that band gap is massive. Okay. If an extreme amount of energy is provided to them, usually through heat, they can have a breakdown voltage and they can be forced to conduct, but you don't really need to know about that. All you need to know is the band gap is massive in an insulator. In a conductor, there isn't really a band gap at all because they can freely sort of move into they're already in the conduction band basically. So in a conductor, there are already outer electrons in the conduction band that are free to move. So the conduction and valence bands overlap as it requires no energy for the electron to reach the conduction band. So there we have an insulator and a conductor in terms of band diagrams. So big gap between valence band and conduction band in the insulator, no gap in the conductor. Semiconductors, as I said, they've got a relatively stable structure, but not as stable as insulators, but way more stable than conductors. So semiconductors can be made to conduct more easily than insulators. So their band gap is actually a lot smaller than an insulator. Okay, and this means they can be made to conduct by adding stimuli, so light or heat, for example, so electrons have more energy to overcome the band gap. And the band gap of a semiconductor can also be decreased by adding impurities to it. So to make a semiconductor conduct, you can either give the electron here some extra energy so they can jump up, so in terms of light or heat, so temperature-dependent resistors, light-dependent resistors, they're semiconductors. So if you give the electrons here light, then they've got more energy to jump up. So they conduct better, so the resistance decreases, light up, resistance down. You can also dope the semiconductors by adding impurity atoms. And what happens there is it actually decreases the band gap. So again, it's easier for electrons to jump up. So thermistors and LDRs, both applications of semiconductors. So how do we dope semiconductors? There are two ways we can do it. One is make a hole, make a space where an electron might have been, or one is add in extra electrons that can't get bonded. So pure, we call it intrinsic silicon, which means just pure. The atoms are bonded together strongly. So we've got, each atom's got 4 electrons around the outside, and each one of those electrons forms a bond with another electron on the outside of another atom. So they all form this sort of very stable structure. Okay, so atoms are bonded together strongly as they share electrons with other silicon atoms to fill up energy levels. Each silicon atom shares its outer electrons with neighbouring atoms. And in pure silicon, all the outer electrons are paired off, and this is a relatively stable structure. You can, again, if you give it enough energy, make it conduct. But a lot easier is we can introduce atoms to make silicon impure and help it conduct, called doping. So N-type doping is when you have negative electrons in the conduction band. It's not very catchy, I know, but that's basically what N-type doping is. So what we do here is we've got our pure silicon, we introduce an atom which instead of 4 electrons in the outer energy level, it's got 5. So 4 of them get bonded up as normal, but we've got this free electron left over. And that free electron can then move around. It's easy for it to move So an atom is introduced with an extra electron. So for example, phosphorus, which has 5 electrons in its outer energy level. This gives it 3 electrons that aren't bonded and can now conduct electricity when a voltage is applied. This means there are electrons now in the conduction band. So here we have the pure intrinsic semiconductor. We've got conduction and valence band. Here we have an N-type, so represented by some electrons. These dots here are in the conduction band, so they can move around these extra electrons. The dotted line, you don't need to worry about this, but it's called a Fermi layer. So that basically means where electrons are on average. So in a pure one, there's like the energy of electrons around about midway between the bands. But because we've got electrons here and here, it's shifted in the don't need to worry too much about that. P-type doping, positive holes in the valence band. So this one, we've got electrons in the conduction band. This one, we introduce an atom with 1 fewer electron. Okay, so with 3 electrons in the outer energy level. So all 3 of those get bonded up, but we've got this hole, this space. Okay, and that means we can have electrons jumping into it. Okay, so we can have movement of electrons because they can move into the hole and leave the hole behind. So an atom is introduced with 1 fewer electron, for example, boron, gives rise to a hole where an electron would have previously been bonded. It now means that other electrons can move into this hole. And since the hole attracts electrons into it, so electrons can move into it, it behaves as if it has a positive charge. Obviously, it doesn't have a positive charge, it's just a nothingness, but it acts like a positive charge would do. This means there are holes in the valence band, so electrons can move within the valence band and conduction can occur when a voltage is applied. So, this is our N-type, so we've got negative electrons in the conduction band. Our P-type, these are holes. Okay, so we've got these holes within the valence band. And if an electron moves here, it leaves the hole behind. But I think that hole moves in the opposite direction of the electron. P-type and N-type semiconductors are still neutral overall, since there are the same number of protons and electrons overall. Okay, so even though we've got a hole there, this atom here has got 3 electrons and 3 protons. Okay, so they cancel each other out overall. And these type of semiconductors are most useful when they're used together. Okay, so in p-n junctions, so like diodes. Right, any questions so far? I'll take a little break myself. Right, okay. So, putting these two together. So a p-n junction is what it says on the tin, a p and an n-type together. Okay, so here's our p-type with our positive poles. Here's our n-type with our negative extra electrons in the conduction band. So what happens when you first put them together is this electron will fill that hole, this electron will fill that hole, this electron will fill that hole. So the electrons near to the holes will fill them in. Okay, just naturally, because that's what electrons do. So some of the electrons from the n-type diffuse into the junction to fill some of the holes in the p-type. This leaves us with a depletion layer either side of the junction where the charges have been lost. So here we go. So the electron from here has filled the hole here. The electron from here has filled the hole here. So we've got this layer here where actually there's no electrons anymore. There's no free electrons because they filled the holes. And there's no holes because they've been filled by the electrons. So that depletion layer there, that kind of stops the conduction happening. Which is like saying, well, why is that happening? Okay, so that basically is a barrier to any conduction. So this layer acts like an insulator as it's effectively lost the charge carriers. And one side has become overall negative because it's gained electrons, and one side overall positive. It now opposes further flow of charge carriers across the junction. We call it a potential barrier. So to overcome that, what we do is we need to apply a voltage. We need to apply voltage that will let these electrons jump over this gap and fill these holes. Okay? So to do that, what we need is we need a positive charge on this side, a big enough positive charge on this side to attract them, and a big enough negative charge on this side to repel them over this little sort of barrier that we've produced. So to get it to conduct electricity, we need negative on this side and positive on this side. It has to be big enough as well for it to overcome that barrier. It can't just be a tiny little voltage, it has to be big enough. So for this material to conduct, it needs to be supplied with enough energy to overcome the potential barrier. To do this, it needs to be supplied with a big enough voltage connected the correct way around. So for the electrons in the N-type material to overcome the depletion layer barrier and fill the holes in the P-type, the opposite side of it, a big enough positive charge needs to be at the hole side. So if a big enough power supply is set up that the positive end of the power supply is attached to the P-type, to this side, and the negative supply is connected to the N-type, this side, the electrons from the N-type can be given enough energy to jump the barrier. And usually, this requires that special number there, 0.7 volts. Now, we've seen this before in transistors last year. And transistors, funnily enough, are PN junctions. Okay, so for the transistor to turn on, to start conducting electricity, 0.7 volts has to be applied in the correct way around for these electrons to jump the barrier and start flowing. Okay, so about 0.7 volts is usually when they start conducting. Not always, sometimes it's slightly different depending on the material, but usually. So that is called forward bias when it's connected the correct way around. If it's connected the wrong way around, it's called reverse bias. So if the power supply is set up the wrong way, the barrier just gets bigger and bigger. So basically, if you set it up this way, then the electrons they're not getting attracted this way, they're getting basically pushed back again. So we're just making this barrier bigger. So only a very small leakage current might happen from the pure silicon. It might eventually break down and damage the component. So this next diagram looks a lot more complicated than it actually is. So in terms of band theory, if we line up the Fermi levels, remember that was sort of the energy that the average energy of electrons, the P-type and N-type bands. So look at these dots. Okay, we've got P-type semiconductor here, we've got an N-type semiconductor here. If we line up these dots, basically this whole thing gets moved down. So the dots will line up. So a conduction band on this side, on our N-type and our valence band, get pushed down. And that is what this is here. So that's our conduction band and valence band. And our conduction band and valence band got pushed down. So this is conduction band, and this is valence band. Okay. And you'll see if we join those up, there's this little hill. Okay. And this is like a hill to overcome. So you'll see there's some work here as well. You don't really need to know drift is the side that the electrons would normally be on. And diffusion is just the natural filling of holes. Okay, so we'll do that direction there. So we've got this hill of energy now to overcome for electrons for any energy to flow, for a current to flow. So if we apply a voltage in the correct way around, what happens is this hill gets less steep, so less difficult to overcome. And that's all that is, basically, in terms of band diagrams. It's basically what we said earlier in words, but we push these conduction layers down, join them up with that hill. If we apply a voltage the correct way around, the hill decreases. And last page of me talking. Practical uses, LEDs. There was a question on LED on the sort of particle and waves revision test I made you do, so some people were not sure how to do that, and some people did well. So, when a PN junction is forward biased, the electrons in the N-type move and fill the holes in the P-type. This means they drop down an energy level. So remember, in n-type, we've got electrons in the conduction band. Then they fill in those holes. So what the holes are in the valence band, so they drop down an energy level to fill those holes. And when they do that, they give out energy. Because they've got too much energy up here, they need to get rid of it so they can exist in this energy band. So they give it out. And usually it's heat that they give out, that heat energy, but in an LED it's light energy. Okay, so they drop down an energy level and therefore have to release energy. This is usually as heat, but in LEDs it is in the form of light. The frequency of light is corresponding to the energy difference of the levels. So your spectrum booklet, they're linked by the equation E equals HF. So if you wanted to know the frequency of that light, find the energy difference here, then you use the equation E equals HF to find the frequency. And photodiodes, so they're either photodiodes or either solar cells or light sensors, depending on which way around you connect them. So photodiodes, photovoltaic modes is like solar cells or solar panels. So photovoltaic mode is when they're used as a source of electricity. So they're not actually connected to a power supply themselves. They're used as a power supply. So photodiodes aren't just PN junctions, they're what we call PIN junctions. So you've got P-type with an intrinsic semiconductor, so pure semiconductor in the middle, very thin piece, and an N-type next to it. So if light falls on the intrinsic semiconductor, it excites an electron up to a higher energy level, which leaves a hole in the lower energy level. The electron moves into the N-type and the hole into the P-type. This separation of the charges produces an EMF, a voltage. Light falling on photovoltaic photodiodes creates a voltage. If the intensity of light increases, more photons release more electron hole pairs, so it gives a bigger voltage. And if they're connected the correct way around and we use enough of these, we can use them to power something. Photoconductive mode is light sensors or light gates. So again, we've got PIN junction. Connect it the wrong way around, so reverse biased. When light falls on the intrinsic part in the middle, it still releases an electron and forms this electron hole pair, and they can still move and create a small leakage current. Increasing the intensity of light increases the electron hole pairs, so it increases the very small leakage current. So this helps them act like a light sensor. So the more light that falls on them, the more current you get, so you can tell how much light there is. And the electron hole pairs in these recombine rapidly, so they react very quickly to changes in light intensity, which also makes them good for light gates when timing things. And that is it. That's everything you need to know on semiconductors. So are there any questions? I think your best bet is to start doing sort of question booklet, like work through your question booklet and just ask me if you have any. If you brought your question booklet, excellent. If you didn't, I printed off the question booklet there. It's next to the theory booklet, so you can grab yourself a copy of that. And we can just spend the rest of today doing questions.